So good morning, everyone, and welcome to this session on space and time complexity. So this is a multi-session talk, and we'll be looking at how to calculate space and time complexity for algorithms, and for basic algorithms, and for later on towards recursive algorithms and more advanced code. So let's look at some terminology before we begin the understand the analysis of algorithms. So what is an algorithm? Basically, an algorithm is a step-by-step instruction to solve a well-defined problem. Algorithm may take in an input, it processes that input, and it generates an output. That's all an algorithm is. Algorithms have existed before even computers existed, and with computers in place, we have a lot more algorithms now. What is a program? Basically, a program is an encoding of algorithm in some programming language so that computers can understand it. And finally, data structures. Data structures are basically a way to store data, right? It's a data storage format in which you can store a data, efficiently manipulate the data as your algorithm is running over the input to process some output. That's a data structures. So just wanted to get this clear before we jump into the real thing here. So this is what it boils down to. How do we compare two programs? How do we do that? I suppose I ask a problem to a whole class of, let's say, whatever, 6-7 people right now. All of you will write code, but how do we compare with what code is better than the other code? And how do we find out how it will fare well on the input size? When we are new to programming, and not even when we are new to programming, when we're writing code, there are a bunch of ways in which you compare programs. So one is basically, this is from the perspective of human beings, right? Which program is more readable? Which piece of code is more readable? This is important because it's very important to manage the code life. And basically, when your code is big, it should be very readable. But once again, it's if a code is not well written, suppose my variable names are not proper, my functions are not proper, because of which my code is not really manageable. But from the computer's perspective, it is completely fine. Computer doesn't care those things. So readability cannot be used as source of comparison when it comes to analyzing algorithms. It's a very good thing, but it cannot be used to compare to algorithms. Can program written in different languages be used as a point of comparison? Sure, it can. To some extent, it can, but it cannot be objectively used to compare two algorithms. So a better algorithm in a slow programming language will eventually beat a fast algorithm in a weak algorithm in a fast programming language. By fast, I mean languages which are compiled, which basically directly run on hardware. So we have all these, but they cannot be used as a tool to compare to different algorithms. So programs written on different platforms. So that's a difficulty actually. I may have a program which runs, let's say, on good on a hardware device, on a desktop machine, but may not run well on a mobile. So that kind of thing. Can we compare based on the platform it's written? Once again, yes, you can, but that's once again not the objective comparison of a program. So can we measure performance metrics like execution time? Is it possible that what we can do is, for example, in Python, right, we have time module, time it, and what we can do is put time in before and after our function executes, and we can run it and calculate time. In fact, we do that all the time in every single software company that's done. However, that also depends on a lot of things. That depends on the environment that you're in, the platform, the time of the day, how much system load is already there, so that computer CPU cycles, are they free to process your program or not? So while this is good metric to understand, for example, if you have an API, how well it's performing under certain situations, it cannot be used really to compare two different pieces of code, like in terms of algorithms. All of these things can be used to some extent, but they don't give a good comprehensive understanding. If I tell you that I have written a very good algorithm, which on my MacBook runs in this much amount of time, that will not really tell you anything, whether this program will run, how efficiently this program will run on a server or on a mobile phone. Let's understand this. Okay. Suppose we have a function. Suppose we have a program. And just give me a second. Let me see the chat. Yes. So suppose we have a function. Suppose we have a script which basically calculates the sum of first n numbers. Okay. Now, what is first n numbers? Let's look at that. Let me just quickly. Give me a second. So let's look at this. Just give me a second. Okay. So now it's working. Okay. Suppose I was to ask you to write a program which would compute the sum of first n numbers. 1, 2, 3, 4, 5, and then whatever n numbers are. Suppose I was to ask you this. There is a mathematical formula to compute the numbers, but suppose that I choose a way to write this as a for loop in which basically I have a total and which initializes to 0, and then I just write a for loop, something like for whatever, each iterator for x in whatever this range is, total plus equals x. And then in the end, I just return the total. Suppose this is the kind of program that I go with. So let's see. What I'm going to do is, in order to measure the time, I'm going to take a snapshot of time here, and I'm going to take a snapshot of the time here. So this will be like, say, time 1, this is time 2. And then in the end, I'm going to compute time 2 minus time 1 to find out how much time is it going to take for my program to run. So somebody asked me to do this. I came up with this piece of code that I'm going to do this thing. So this is total equals to 0. Then I start my timer. This is basically, I'm using Python code right now, but don't worry about the details. Then I'm writing for I in this loop, calculate the total by adding the total to the current total, and then end that time, and then return the total and the end start. So that's one way of doing it, right? But somebody has written this piece of code. Let's say another person has written another piece of code, which is this, version number 2. So this is sum of n2 again, in which now I'm using a formula to compute the same piece of code. Mathematically, we know that if there are numbers 1, 2, 3 to n, the sum of these numbers, right? The sum of these numbers is equals to n into n plus 1 by 2. that is the formula to compute the sum of the first n numbers. Suppose I just directly use that formula to compute the sum here. Okay, so I'm just no for loop, nothing. I just start a timer, then I compute an operation here, and then I end the timer, and then I report the total and end minus start. Suppose I just wanted to do that. So what I've done is I have written this script already. Let me show you where the script is. It's here. So you have two functions, sum of n, which is calculating the method number 1, and this is number 2, method number 2. So this is operation here, and this is the first loop. So now we have an input. So let me just reduce the size of input to, let's say, 100 for now. Okay, and let me compress this guy so I can open my terminal on the other side. Okay, there you go. So we have the sum of n. So we run this for the first input. The first input is right now 100. So what is happening here is we have an input of 100. We run the first piece of code, and then we just run it 5 times. So how we do benchmarking is that we take a test case, we run it n number of times, and then we calculate time, and then we average that time. So essentially, for the first input, I call sum of n on the input, which is 100 at the moment, and then I run this 5 times. Then I calculate the average, basically. Here I'm not calculating average, but I'm just printing it. So this is gonna output the sum and the time it's gonna take. First it's gonna run the algorithm number 1, then it's gonna run the algorithm number 2. Okay, so as you can see, for the first 100 numbers, algorithm 1 for the first 5 attempts is taking this much amount of time here. And you can notice it's in microseconds at the moment. And the other algorithm is showing this time. So what I'm going to do is I'm going to change the script a bit and maybe make it 10,000. Something like this. I'm going to run it again. Now you will see a clear difference coming not to the human eye, but in the form of, but to the computer's eye, because computers, all of this matters. So this is now in the order of, what is this, millisecond? Yes. And the other operation, the other algorithm is continuing to perform at the same scale, at the same microsecond level. Let's go here and increase this a bit further. So this is now a million, right? Yeah, this is a million now. So for a million input, when we run this, now you can see the algorithm number 1 is now lagging behind by the order of 10 to the power 5 at the moment, compared to the second. Let's take this a bit further and just maybe make it one more. Run this. Now algorithm 1 is taking 1 second, okay, 1.5 seconds around. And the algorithm number 2 is basically still performing on the same scale. So when we look at this 2 piece of code, if I increase one more, it's going to take considerable amount of time. What I'll do is I'll just leave it here. What is this input size? So this is million, billion, right? So this is let's just make it a billion. Put 9 zeros in front. Let's just make it a billion and let it run. It's going to take some time for the algorithm number 1 to run, and we'll come back here. But essentially what happens here is we can get this idea what is happening. These are the two pieces of code that we want to compare. The one piece of code is computing the entire result in just one operation, and the one operation is here. The other piece of code basically is computing the result by doing a computation n number of times, right? So if the input size is, let's say, 1000, then this operation here will be repeating 1000 times. Whereas in the other piece of code, this operation is independent of the input size. It's always just one operation regardless of the number of times, the value of n is. So that's a type of comparison that we probably want to do. Now, once again, if I take this piece of code, run on different platform, it will show a different time. But let's come to the point where how can we objectively measure the performance of an algorithm? Meanwhile, let's check how this algorithm is doing here. It's still computing right now. It's probably going to take some time to compute. So we come to a new definition of comparing algorithms, which is the resource usage of algorithm. So comparing the algorithm based on the amount of computing resources that algorithm is going to use. Okay, not measuring the time, not worrying about the platform or the programming language, but something that I can tell you when you are in the other corner of the world. I can just tell you based on the computing resources that this algorithm is going to consume, that how good this algorithm is. How do we do that? Let's talk about it. So basically, that is called analyzing algorithm efficiency, which is independent of the platform and programming. Now, the first measure that we have is computing the number of operations as the function of input size. So given a computer, so for input of size n, how many operations will your algorithm need to do in order to generate a result? That's what this means. So as a function of input size n, how many operations is it going to take for your code to generate a valid result? For the previous code here, right, we had the sum version 1 and we had the sum version 2. It took an input of size n. Actually, this input of size n is just a number, but you can just say n, okay. Given the size of input n, this ran a loop for I like equals to 1 to n, and then sum I to total. That's what this was. And this is a formula where this is saying n into n plus 1 by 2 and just return that value. So if the input size is 1 here, then version 1 and version 2 will take 1 and 1 operation. They'll be same, essentially. The code will not be different. Now, if the input size is 2, this will be 2, this will be 1 still, because we are only doing one operation here. If this is 1000, this will be 1000 operations, but this will be one operation. If this is a 1 billion, then this will be 1 billion operations, and this is still one operation. If your computer is processing, let's say, 1 billion operations per second, let's say that's what your computer is producing. Let me just not confuse this with this. B can be confused with bits. So 1 billion per second, then essentially here it will take 1 second to compute this guy. 1 second. But this is only one operation, so 10 to the power or whatever minus 9 order operation will be computed. But once again, I'm not concerned about this time here. All I'm concerned about is how this algorithm is going with respect to the input. So if I was to draw a graph of the function number 1 here, let's take the function number 1, which is growing as the size of input. So if for any input of size n, this function roughly takes n operations. Here, this side is operations. number of operations, and this is input size. And for the other script that I have here, maybe it is just doing one operation. So if this is 0.1 here, then it is going like this. Let me use a different pen to draw this. If this is 1, then basically we are going at the similar regardless of the input size. For any input size, we are just constant time. So that's the difference between the two algorithms. So what do we call this? This is rate of growth of operations as a function of input size. So that's one measure. And the other measure is similarly, how do we use memory? I've not talked about memory yet for the previous function, but we'll talk about it later on. If you guys have any question, you can ask me on microphone because I've muted my chat. So now time and space complexity again. Once again, it is computing algorithm based on the computing resources used. So in the previous case, this computing resource is the CPU cycles. How much effort the CPU has to make in order to compute your output. Simple example it was. Now analyze algorithms efficiency, basically independent of the platform and programming. So I may now give you an algorithm and tell you that this algorithm is basically a linear time algorithm, something like something like the previous algorithm. This will give you an idea that as you increase the input size, the number of operations needed to compute will grow linearly with the input size, like this. I have drawn something which is like a 45-degree slope here, and it looks like it's 1-to-1. It may be something else. It can be, let's say, a 10n, right? For the input size of n, it's 10 multiplied by n. So the code may be some linear slope, may be something like this, or it can be less than this. It can be something like this, n by 2. But essentially, they are all linear. And finally, most important thing, time complexity is not about measuring time. This is one important thing to understand. The name is called time complexity, but it's actually, you're not literally benchmarking or measuring time for anything. This is what time complexity is. Order of growth of number of operations as function of input size. This is also referred to as asymptotic analysis, right? So what is an asymptotic analysis? When we compare the two algorithms there, if we make the input size sufficiently large, then the only thing that will matter is the amount, the value of the input size, how big the input size is. And rest all the constant factors will go away. And this we will see an example shortly. And at that point of time, you can literally say how your rate of growth is dependent on the input size. And when you analyze your algorithm, you can express things in the form of worst case, average case, and best case. Let's come to this. Suppose that I am to write an algorithm for searching. Okay, suppose that I have a list of numbers. Okay, list of numbers is something like, let's say 5, 51, 14, 7, 95, 101, something like this. There's an array called A, which is this. And let's say that there is a value V. Okay, some value. Let's say it's basically at the moment is 14 or something. And we have been asked to write a function that will check whether this value is present in this array or not. And if it's present in the array, then basically return the index. If it's not present in the array, then return something like maybe a nil or something like that. Nil or -1. Something like this. Okay, so how do we do this problem? Let's just quickly write some pseudocode for this problem. Okay. My routine is called search, and search is going to take an input size of, let's say, an array and a value, something like this. Something like search array with a value v. So what I'm going to say here is I'm going to write some kind of a routine. So I'm just going to say for I equals, let's say, 1 to a dot length. Right. So for starting from the index 0 here, 0, 1, 2, 3, 4, and 5. So starting with my mistake. So I'm just analyzing algorithm. I don't need to be specific with the index. I can just write 1, 2, 3, 4, whatever. I don't care right now to make it simple at the moment. I'm just writing from 1 to whatever the array dot length is. We can check if a particular number is equals to the value present. So we can just check if a of I equals v. Right. Once again, I'm using just one equal. I'm writing pseudocode. I'm not worrying too much. Actually, let me put it like this. So if that is the case, then basically return I. So this, what I'm doing here is my loop is going to run from 1 to a dot length. And for each index, I'm going to see the value of array by writing a of I and check if that is equals to v. If that is case, then return I. But if I run out of the loop, then basically I will return a nil. That would essentially mean that I have not found anything. In this case, if I run out of the for loop, that is, if I go from here, then here, all the way till here, and I have not been able to return a successful, that means the array has exhausted and I have not been able to find, the right answer here in this case. So I will return a nil. Give me a second. So suppose that is the algorithm that we have written here. And I'm giving this algorithm to you. Now the question is, how do you analyze this algorithm? How do we go about analyzing this algorithm? So what we do is this common practice. Okay, I'm going to introduce some spaces here, and then maybe let me just introduce some spaces between each line, then take a screenshot of this. Okay, so let's take this. Suppose this is my piece of code. Okay, now, as I mentioned, we are interested in the analysis of the number of operations this is going to take for my task to actually compute. So how do I calculate that? I'm going to go over each of these lines and compute the number of times they are going to repeat. I mean, they're going to execute. So how do I do that? The first metrics is that I'm going to use is something called cost. So why is cost important? So cost means that in order to perform this operation, this is the cost included, that this is the cost of that operation, which can be some constant. And the second item is times. How many number of times is this statement executing? Okay. Suppose that in order to run the for loop, each statement of for loop, there is an associated cost C1. Okay. Each time the for loop executes, this much amount of CPU cycles are waste, or this much amount of whatever other energy is waste. So how many times does this statement execute? If the array is of, let's say, size n, then this will execute the whole size of n plus maybe one more. When the loop terminates, I can write n or n plus 1. I'm writing n times. If this is executing n times, then how many times will this execute? Let's say if the cost of doing an if operation is C2, then how many times does this operation execute? If for each time in the loop, I'm going to execute this, so this is also n times. This is one way of writing this. Or you can think of it that it will execute one for each loop, where the loop will be I equals to 1 to n. And this will evaluate to n as well. You can write it this way, but that's okay. Let's just get rid of it. Keep it simple for now. How many times, let's say the cost for this is C3. How many times will this operation execute? Exactly one time, right? Exactly one time it's going to execute. And how many times this operation going to execute? C4 cost, one time. It is not certain whether we will reach this or this, one of the track we will reach, but it will be executed one time exactly, not more than one time. So the total cost can be written as a summation of all this. So it can be written as C1 of n plus C2 of n plus C3 plus C4. So this you can write it as equals to C1 plus C2 of n plus C3 plus C4, something like this. This essentially is some form of an plus b, right? So we are saying how whatever these costs are, whatever these small costs are, maybe some CPU cycles or whatever, given the n is large enough, the output will really depend linearly on this input. We can express that our binary search, sorry, not binary search, just a search function for a size of n, for the input size of n, is dependent, basically will perform some operations proportional to n. So the function that we can express is basically, function to express the time complexity would be something like an plus b. If we were to plot this function, okay, if you were to plot this function, suppose what I'm going to do is, let me get rid of this. If we were to plot this function now, suppose this is input and this is output. Oh, sorry, this is operations. And this would be b here, and it will go like something like this. That means something like a linear function here, an plus b, where if the size is 0, then you have this b. This is b. And if there is some size, then basically you have b plus an. So an is growing in this way. So once again, this is a linear graph, right? We know that I'm going to give you the search algorithm, and I'm going to tell you that with respect to the input, my algorithm will compute and give you the result back as a function of linear complexity. So basically, it's linearly dependent on the input size. This is what I'm trying to say, sorry. Yeah. Any questions?
Himanshu, C1 and C2, like C1 and C2, like you added them, right? Like, when I generally when you have multiple loops, you multiply. So why here we don't multiply and add? And if suppose A of I was a list or something like a bigger list, how it would react? Like suppose you're searching in a list or dictionary, it is the same thing, right?
So first of all, the C1n plus C2n, right? We can take the n as common and then add C1 plus C2, right?
So we don't loop or multiply it, right? Like, one into the other, like.
Why do we loop and multiply into one or the other? So
adding direct.
no, so if you go to my previous, let me go back if I can. Let's see if I can go back to that level. Maybe I will be able to. Let's see. Yes. So this is what we have computed, right? These are the total number of operations that are going to take place in order to compute. Correct? So we take this plus this plus this plus this, right? So this is multiplication. C1 is n. C1 is or cost is repeating n number of times. So it's C1n. Then you have C2n. But then you plus these two things, right? They are not going to multiply amongst each other.
Himanshu, have a question like the cost even does it correspond to this for loop and C2 corresponds to if statement?
Yes, exactly. Think of cost as something which is independent for that operation. Suppose that I have a operation A plus B, right? I write to computer 5 plus 9. It is not a free operation, right? Computer has some cost for it. So I'm just writing it as C1. If this operation is repeating n times, then the cost will be n into C1. Essentially, that I'm writing. So in the previous case, if you go back, maybe not.
And you took the worst case, right? For the if condition, like in general, you take the worst case.
So I'm coming to that. So let's go back to the code again. I'm coming back to that now. In this slide, we talked about we ended that slide with the case analysis, right? So suppose I'm going to move this again here. In the previous slide, I stopped at this point. Worst, average, and best case. So let's look at that. What that means, really. So once again, I quickly repeating, each operation has a cost. In order to, let's say, compare, there is a cost associated with it. So I'm writing the cost here and the number of times that operation is repeating. So this cost is C1, C2, C3, and C4. And this is repeating n times, one time. Then essentially you can write your algorithm as an plus b, which is what I'm writing is something like this. C1 plus C2 of n plus C3 plus C4. Suppose I'm writing this algorithm, okay, and I've given it to you now. So now people are thinking, okay, this is a linear time algorithm, but let's analyze the complexity in different types of input. Suppose that there is an array here, and with array is 10, 5, 15, 36, 91, 2, 10, something like this. Suppose this is the array. If our input, let's think about the best case scenario. What will be the best case scenario in this situation? What do you guys think?
We find the element at the first position. The target element is found in the first position.
Yes, exactly. That's the best case scenario right now. So every time we go look for our key, it's found in the very first iteration, right? So in that, if this is the found in very first iteration, okay? So what will happen is, I'm just writing this as best case. This will execute exactly one time. This will execute exactly one time. This will execute exactly one time, right? So our time complexity, which is like this, n will be 1. So it will be a plus b, which is a constant time complexity, right? The best case is that it can be a constant time complexity. In this case situation, in the best case, if we always find in the first iteration, then we don't need to run the whole loop. Things will execute on the very first time. What can be the worst case here? What do you guys think?
The element.
Either we don't find the element or we find the last element. It's always the last element, or we don't find it. So in that case, our program will have to exhaust the loop completely. So this will execute n times, this will execute n times, one time. So in this case, our time complexity would be an plus b, and this will be complete linear time complexity in that case. Let's look at the average case situation. What can we assume for an average case?
We find in between or somewhere in the array.
Sometimes it's found in the first position, sometimes found in the last position, but we can say average, it will be found n by 2th place. Okay, let's just say that. So in that case, this will execute n by 2 number of times. This will execute n by 2 number of times. This will be 1 time. This will be 1 time, something like this. So in this case, our time complexity will be a and n by 2 plus b. So this is this guy, this is this guy, and this is this guy. Once again, this is again linear time complexity. Both of them are linear time complexity. If you draw the plot of these three functions, so all that will happen is that I'm going to get rid of this slide. Let me just copy it in case I need it later on. If we were to draw the plot these three graphs here, okay, this is input and this is output. The best case scenario was that we are only going to operate constant, right? We always find at the first location. So if this is the point B here, then the best case scenario is this guy. Best case. That's the best case scenario. If we were to say the worst case scenario is denoted by, let's say, red, which was an plus b. So it is something of this sort. Worst case. And if we were to say average case, which let's say is denoted by the gray, then it would be something like this. This is an by 2 plus b, something like this.
Hey, Imanshu, it's operations, right? Y-axis.
Yes.
Okay.
Operations. I'm so mistake. I just keep doing this mistake. My mistake. Thank you for correcting. Let me put it here. Operations. That's the average case situation here. So asymptotically, let's come back to the definition of asymptotic. Okay. When the input size is large enough that only the order of growth is time relevant, right? All the constants drop out when the input size is large enough. I'll show you the graph basically on a website, so it will become more clear. But if the input size is huge, if n is very, very big than 1, it's superbly big than 1, then this an and an by 2 will not matter at that point. There will be no difference in this. I mean, they will pretty much be equal in that case. And both of this is linear situation. So you will say the worst case is linear, average case is linear, and this is best case is constant. Now, how do we express this? When we have derived this, suppose that our time function, which takes in an input in the terms of n, right, and generates an output, basically it tells you that it is, let's say, an plus b or something like that. Suppose this is the relationship right now, an plus b. Then how do we express this? When I give you my code, the convention to express this is by notations. So the notations for the best case is this. For the average case, it is this. And for the worst case, it is this. This is like a big O. So I will write, but that my algorithm is not an plus b, but O of n. That is, it is linearly dependent. So once again, if the size of n is huge, a and b will not matter. Essentially, that's what I'm saying. For the average case, it is theta of n. And for the worst, so for the best case, it is this. Best case. When we are preparing, let's say, generally when we are doing, all of this is very important when we study algorithms, like an algorithm class algorithm. But if we are preparing for the interviews, the real thing that matters is this guy. We should be able to understand what this guy is. We can literally express everything as O. Even when somebody asks what is the average case, you can say O of whatever n. You can say that. By graph, what does this mean? Let me show you. By graph, what this means. Suppose that you have a graph again. And suppose this is your, let me draw a better graph. Suppose this is your time complexity. It's going some weird thing like this. Then the best case is this guy. And the worst case is this guy. That's what this is. Whenever we face an interview situation, just quickly say, you always express your answer in the form of worst case. Right? You will just say, okay, this is O of n. Don't worry about it. The best case, average case. You should know about, theoretically, you should understand what the best case would be in a given situation. I'm going to take one more example right now. Theoretically, you should understand what the best case is, what an average case would be, but the answer is usually expected in the worst case. Any questions, first of all?
I've seen like linear time is also best case is also represented as 0 of 1, not the theta or not with the another sign of 1.
So yeah, so once again, as I mentioned, you don't have to use these signs anywhere.
Okay.
You don't have to use, this is specifically algorithm literature. You can say my best case is O of 1. You can say that. You can say my best case in this particular situation is O of n as well. Some whatever, let's say there's some hypothetical algorithm in which the best case is O of n. You can say that my best case is O of n in that situation.
Okay.
That's what I'm trying to tell you. Yeah.
Yeah, I have a question. Like, say, if we try to extend this one-dimensional to two-dimensional array, right?
Right.
In that case, say we'll have C1 plus C2 plus C3 of n plus, right? It would change, right?
So if you were to,
Have a
you mean a loop with a loop? That's what you're saying, I think.
Yes, because right now we have considered a one-dimensional array. So if we try to think about a two-dimensional array, like a matrix form, like a 2 by 2, in that case, like we'll have a different complexity values, right?
Yeah, exactly. That's correct. So let's take an example. Okay, suppose let's take an example. Let's write pseudocode for one more problem. Okay, this is called, let's say, intersection. Suppose that somebody has asked us to find the intersection between two arrays. Okay, suppose there are two arrays of some sort. Let's say this is array A equals to something, which is basically 3, 5, 9, 10. I don't know why I'm writing in the sorted order. Let me just add a 1 here. And suppose that there's another array, B, and the B is something like 5, 1, 15, 37, something like this. And your task is to return another array C, which is the intersection of both the arrays. Okay, suppose that this is the situation right now. Now, this problem can be solved in many, many ways. Okay, this problem can be solved in many, many ways. But suppose I choose to do it this way. What I'm going to do is, I have a procedure here called intersection. It takes A as input and it takes B as input. What my plan is that I'm going to initialize C to an empty array. Then I'm going to say for I in A dot length, that is for all the items in A, just we pivot on the element number 1, then you write another loop for j in b dot length. So I'm going to take one item in A and then compare with all the items in B to check if there is an intersection. So I'm just going to say if A of I, suppose, equals to B dot J, B of J. If that is the case, then basically C dot, let's say, append A dot I. A of I, sorry, not A dot I. And then in the end, basically just return C. Suppose this is, I'm writing this type of code. Okay. There are better ways to solve this problem, but I'm just intentionally taking up this way. So what am I doing here? First of all, let's understand the algorithm really quickly. You have 2 arrays. And the array number 1 is basically doing some numbers, 1, 9, 3, 2. And the other array is basically something like 5, 7, 5, 2, 7. Then this is A, this is B. My algorithm is saying pivot on A, first element of A, and then scan all of these elements here. If you find this guy, then add it to our common list. Something like, let's say for 1, there is nothing found. For 9, there is nothing found. For 3, there is nothing found. For 2, okay, there is something found. So I'll put 2 here. So for all element of this, we are scanning all of the elements here. Let's say this is what I'm saying. Suppose both the arrays are of same size. Here are their different size. Both the arrays are of same size. The size is n for now. So let's copy this code here and understand the time complexity of this code. Once again, I'm going to introduce some spaces so I can calculate the numbers properly. Suppose I'm going to do that. Let's just take it here. So in this case, once again, we analyze in the same way. We first of all have a cost of each operation. There is some cost to do that particular operation, and then number of times that operation is repeating. Okay. So first of all, I'm going to initialize an array. So the cost of doing that, let's say, is C1. The number of times I'm going to do that is, let's say, 1. Okay. Now I'm going to run this loop for I in A dot length. Suppose both of them are n size. And then we will consider the generic case of them being different size as well. So how many times, let's say the cost, let me just write the cost quickly. Let's say this is the cost for doing all of these operations. How many times is this loop going to execute?
N times.
N times, correct. How many times this loop is going to execute?
N times. More than n times. It will be like for each element, it would be going n times.
N squared?
N square, I think.
So essentially, yes, its an answer is n square. It's going to run n square. But I'm just going to write mathematically that it's going to repeat n number of times, and it's going to repeat n number of times for I equals to 1 to n. Okay. I'll come to that calculation in a second. It's going to run n number of times for each time when I goes from 1 to n. And similarly, this guy here is run the same number of times. I can write it 2 ways. I can say, let me write it the same way. I equals to 1 to n times. And then this guy will run some number of times. Okay. Run some number of times. Let's say it's k number of times. And this will run one number of time. We don't know what this k is. It depends on how many intersections are found. We may have to do this appending operation. We can assume something, maybe n by 2 or whatever later on. That's fine. So k number of times. Now let's just quickly go over some mathematics to understand these. If I have this I equals to 1 to n, and I have I here, what does this mean? Does anybody know?
The lowest range of I is 1 and the maximum range is n.
It is this, right? That's what this means. And if I have, and this is equals to n into n plus 1 by 2, that's what this means. If I have I equals to 1 to n 1, what does that mean?
Just one.
Just one. Yeah.
So this means that whatever this expression is, it's going to be same for each value of I. So this will repeat n number of times. That's what this is, and it will be equal to n. That's what this means. Okay, let's rub this.
Himanshu, how do you do for odd numbers or even numbers? I is equal to 1 to n. You want to only have odd numbers. So do you adjust that over that sigma sign, or do you adjust your I?
You can, yeah, I mean, what you will do is you will write a formula for I there, like 2p plus 1, something like that, to make it an odd number. So let me write the odd number. So if you are specifically looking for odd number, assume this, that you want all the odd numbers to be plus, right? So basically what you'll do is you have a sigma of, let's say I equals to whatever, 1 to n, and then you will write 2 of I plus 1, something like this, or 2 of I minus 1, however you want to compute. So what this will do is, this will be 0. So this first number will be 1. So this becomes 0.
Yeah, okay.
And then it will be 3, like that. So, but okay, let me rub this. So essentially, you guys were correctly right. I just introduced this, so this forms a foundation for you to write this properly. Later on, it might be slightly more complicated. That's why I wrote it in the sigma form. But essentially, everybody was right when they said n square. This, let's evaluate it. This means what? That each time is going to take n operations for I equals to n, right? It's not a function of I. It's n times repeated n times, right? This sigma means 1 to n times. So this becomes n multiplied by n, which is n square. So I'm going to get rid of this and just write n square here. So this becomes n square. This will help you when you do the best case analysis. That's why I wrote this, but it's okay. Let's put it n square. This is n square. So now let's compute the cost. Overall cost of this is going to be what? C1 of 1 plus C2 of n plus C3 of n square plus C4 of n square plus C5 of k times plus C6. That's the overall cost of this. So let's convert this a bit further and say basically this is looking like C3 plus C4 of n square plus C2 of n plus C5 of k plus C1 plus C6. This is something like this. Sorry, I'm lacking the amount of space here, so I'm going in the corners. But essentially what this is you are expressing as a of n square plus bn plus k plus c. This k is not a constant, right? We don't know just how many number of times this is going to happen. This thing is going to happen, so we have called it k. What can be the maximum number of times this can happen?
All the possible elements in the array.
Right, n. Correct? What is the minimum number of times this can happen?
1.
1.
0.
Oh, sorry, yeah, 0. My mistake, 0. What is the average number of time in that case? Maybe n by 2. Let's just take the average case, n by 2. So we can express k as something. Let's take it, whether we choose 0, n by 2 or n. it is not going to matter because we have an n here as well. So let's just take it as n. So essentially in the end, this can be written as a of n square plus b of n plus k plus c. Once again, this can be taken anything. I'm going to take it as n. So this can be written as a of n square plus generally bn plus c. Okay. It will be something like, and I add will be plus something of n and make just call generically calling it bn. So this function, if you notice, has a n square time complexity. So when you express it, the most dominant term here is n square. This is going to dominate your input. If n is very, very large, it's very, very large compared to 1, then this term will become insignificant. This term will become insignificant. Only this term will rule. Even this a, bn square, bnc will become insignificant. And in that case, your complexity of your algorithm generally expressed is O of n square. Any questions here?
Like, what if our n number is like not a single digit, double digit? It is 10, like 10 to the power 9 or 10 to the power 100, like those big numbers.
Right. So, I mean, once again, the complexity will remain the n square. So if it is, let's say, 1 billion, then it will be proportional to 1 billion square.
Okay.
So let's plot the graph of this guy. Now let's plot the graph first. We are a little over time and I'm going to continue for 10 more minutes and then we'll carry on in the next session. So this is how we express the time complexity of a code, right? We express it as a big O notation of some function of n. That's what we do. Some function of n there. These functions can be, the most popular pattern that you'll encounter are, let's say, a linear time, some kind of n to the power something like polynomial time, which is n square, maybe n cube, maybe n to the power 4, and like that. Or it will be something like 2 to the power n. Do you guys know what this is called?
Exponential or something?
Exactly. So this is
Polynomial.
exponential. Or it can be something like, let's say, log of n. It can be something like n log of n. It can be something like n factorial. Or it can be something like O of 1. The 1 means that if you have 1, that essentially means that your output, so the number of operations are independent of the input size. That is, whatever the input size may be, the number of operations are completely independent of that size. We saw an example here. In this case, the number of operations are completely independent of the input size. N can be a billion. We will take only these many number of operations. That first we do a plus, then we do a division, or whatever, multiplication, and first then we do multiplication, then we do a division. It's always be the case. 3 operations, regardless of the input size. So in that case, that is time complexity of O of 1. Let's just quickly look at the graphs of this. Okay, so basically we understand how they look. Let me plot these graphs quickly. Give me a second. I'm going to use something called Desmos. Yes, I'm going to use this. Let's look at the plotting of all of these graphs. Okay, first I'm going to plot something like a constant. Okay, let's put a constant there here by saying y equals to 10. Give me a second. Let's begin with this. This is correct, right? Yes. Give me a second. So first I plotted a constant, then I plotted a linear. For example, this is y equals to x. You can have more type of linear, right? You can have y equals to, let's say, 10x. Essentially what that does is, let me just take this guy here and adjust it a bit. So let's get rid of the grid maybe, and let's get rid of the, this is good. So as you can see, so this is y equals to x, and this is y equals to 10 of x. I hope this not a problem. Let me actually invert the color. Maybe that will be. Let me know if it's easy to view at the moment. So this is y equals to x. Actually, let me go back to this one. Sorry about that. Yeah, this is y equals to 10x. So as you notice, these graphs go in a separate domain, but essentially they are both linear. If I reduce the size, they grow like this. Let's put another graph here, which is, let's say, y equals to x square. Then the graph is something like this. So that is x square. This is x, and this is 10x. So if you notice, for some time, y equals to x is taking more time compared to the square. If the input was, let's say, 0.5 right now, then the square would be less than the x. But as you go further, it doesn't matter. Square is going to beat everything, 10x or whatever the other curve is. It's going to beat all of those curves. There'll be some intersection point, like that is the intersection point, and then x square is going to beat the linear time. So any power will beat the linear eventually. So that's why we say that the n square will always be more expensive compared to a linear time. That's how we'll say. Let's look at some of the other time complexities quickly. I'm going to keep this as curve here. Let's look at y equals to log of x. So that's log of x. You see, it's better than lot of time complexities here. It's performing way better than the linear. And what are these graphs saying here, by the way? They're saying that as this input size is increasing here, these are the number of operations it's going to take. So let's say for 6, log x would be something here. X would be way above, x square would be way above, 10x would be something else. So, but the log is way better. Other good function is, let me see, how do we put it? Power of half or under root? Yeah, under root of x. So that's the another graph, under root of x. Let's put another one here, maybe y equals to x log x. That's x log x. I know it's becoming crowded now, so this is x log x now. X log x, or basically in the end, in the world of algorithms, it's called n log n. The term is called log linear. That is the time complexity called log linear. And then you have some very dangerous things like y equals to x factorial, and y equals to something like, let's say, 2 to the power x, or y equals to x to the power x. These are extremely expensive functions. So if I get rid of this guy, and this guy. Let's get rid of all this. Let's just keep these ones here. So you will notice that's how they're growing right now. So when you generally express algorithms, the number of operations here, basically, they grow like this. The time complexity, when you measure in increasing order for an algorithm, generally expressed, O1 would be the smallest. Doesn't mean O1 will always be the smallest. O1 just means that the number of operations are constant given the input size. There may be 1,000 operations or maybe 1,000,000 operations, but there will always be million. After that, we have O of n, something like this. In between, we have other things as well, by the way. We have under root of n and all that. We'll make it basically O of n square, polynomial time here. And then basically, I think we have 2 to the power n, and then we have n factorial. That's how this will grow. And I think Wikipedia page has a good graph. Asymptotic analysis. Let's see. See, this probably should have a graph. Yeah, there you go. That's the graph I was looking for. So you can compare the algorithms here. They have marked this. Oh, this is O1. And then you have log n. Then you have under root of n. Then you have n. Then you have n log n squared, 2 to the power n, and n factorial. So this is the order in which your algorithm will consume the number of operations. Any further questions? Okay. Now, let me pause the recording and give the future schedule quickly.